Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to be talking about OpenROCKET. Now, a lot of people who've watched my CFD videos have asked if I could do a couple of videos on OpenROCKET, and I'm more than happy to do so. First, bear in mind you might hear some clicking with my microphone. I don't know what's going on, but you might hear it every once in a while, so hopefully it doesn't annoy you guys. Okay, so first off, OpenROCKET is an open source rocket simulation tool. It pretty much is CFD without all the visuals. It calculates drag and all that fun stuff, velocity, apogee, ejection time, everything that you need for a successful rocket launch. Now, I don't pick, you don't need CFD for any of these rockets. OpenROCKET is just fine by itself, but CFD is also nice to have just to see how the fluid of air flows around the rocket, to see the visuals, and also to calculate the forces, which OpenROCKET can do as well. So, OpenROCKET is free, it's open source. What you want to do is go to your manufacturer of the rocket and see if they have what they call a rock sim file. So I'm over here at Apogee and I'm downloading the Zephyr file. So I'm going to go to Zephyr, I'm going to search for it. It's a level 1 kit. I'm going to go to rock sim file, and then I'm going to click it and download it. Now you're probably wondering, hey, why you say RockSim when we're using OpenROCKET? OpenROCKET opens up RockSim files. So you're going to go ahead, download the zip, extract it, and you're going to open up OpenROCKET and go ahead and close that. You're going to go to File, Open. Going to take a few seconds. Yours is going to be empty, and you're going to be wondering, hey, where's my file? You need to change it from OpenROCKET Designs to All Rocket Designs, and then you can see the rocket format. Click it, open it, and then immediately save it as the default OpenROCKET design. So for right now, I've already done that, so I'm going to go ahead and open it, and it's going to do this. Now we're going to just discuss level 1 options today. Next video will be about using this rocket for level 2. Because on their website, it does say you can use the J270 motor for this for a level 2 flight. We'll deal with that later. Let's talk about some basics first. Up here, you'll see the bill of materials. You'll notice nose cone, body tube, tube coupler, parachute, some sort of mass something, and when you click each one, it is bold here. However, notice this picture. It shows an airframe, another airframe, and it looks like a string. Most likely that's probably the shock cord. So go ahead and double click it, and lo and behold, it is shock cord. So I don't know why they named it this way, but go ahead and rename it to shock cord. And then this body tube is that one. And then you'll notice this body tube right here is something that fits inside of this body tube. And you click it, this one is in bold. That is the motor mount tube. So we're going to right click, edit, or double click, and you're going to call it the motor tube. That way we can know what we're picking when we do motor selection. Okay, so let's look at the fin set. I'm going to double click it. It tells you there's 3 fins, tells you the type of material, and it's got smooth paint. You can always change that if you want to do some calculations, because notice it says 20 micrometers. That is used for the drag coefficient calculation. We'll discuss that here in a bit. They're 1/4 inch thick, made from aircraft plywood. There is no fillet. You can always add a fillet of epoxy, and you can go ahead and put that in there, but we don't need to worry about that right now. The shape, this is the shape of the fins. This is the coordinates. This coordinate is important because you can export these coordinates as a CSV, and then you can 3D print them or laser cut them, but I'll show you how to do that later. Actually, I won't. I'll do this. Right click, export as OBJ. You can export the fins as a mesh and 3D print them, or open them in a laser cutter and cut your own. Sorry about that. Okay, you can do that with the nose cone as well. Don't know about the body tube. Oh, the body tube. So if you want to 3D print the body tube, go for it. Parachute. If you want to 3D print the parachute, that's great. Okay, so let's talk about this blue dot and this red dot. If you look up here, that's your center of gravity and center of pressure. Center of pressure should always remain behind the center of gravity by at least a stability of 1 caliber. What that means is if you have airframe diameter of 4 inches, 1 caliber is 1 times the diameter of your airframe. So if this says 2 calibers, that would be 2 times the diameter, but it's 1.64, so it's 1.64 times the diameter, which means whatever that number is how far your center of pressure is from your gravity, your center of gravity. Notice the location is 43 inches. That is from the tip to here. These are calculated from the Barman equations, which you can look that up and learn how to do it for each component. Speaking of that, let's go to Tools, Component Analysis. Right now the Mach number is set to 0.8, which is really high. We'll change that here in a minute. If we go to drag characteristics, it tells us that the total drag is 0.542, and it looks like right now friction, drag due to friction, the air moving over the components, is the main culprit because it's a little bit higher than pressure, but pressure drag is catching up. If we were to change that Mach number by going to Edit, Preferences, Design, let's change that to the default, which is usually 0.3. Drag this up, hit OK. Go back to Tools, Component Analysis, Mach numbers back down to there. Drag characteristics are, drag coefficient is now 0.45. Friction is 0.19, pressure is 0.123. So for small Mach numbers, friction due to the air resistance is the main culprit. But as soon as you start hitting supersonic flight, the pressure drag is what dominates in the calculations. So stability, you can see where each component has its stability measured at. Some of them are 0 because probably, I don't know why they're 0. They probably because they're on the inside and not needed. Okay, so that is how stability works. Let's go over to side view and switch it to 3D unfinished. Left click, hold, rotate, up and down, left and right, do the thing, kind of gives you an idea of what's up. This is our parachute, obviously the nose cone, motor tube, motor mounts, or centering rings, depending on what you want to call it. The coupler, which I don't know if this coupler could be used as a avionics bay. Notice there's no information about max velocity, acceleration, or how high. We do know it's almost 5 feet in length. It's a 4-inch diameter. So let's add some motors to this. Go to motor configuration. Notice it says motor tube. Now if it would have said body tube like before, we wouldn't have known which one to pick. So motor tube is selected. I'm going to go to 3D unfinished, back to side view. Excuse me, sorry. Click once on new configuration. We're going to go find the H283. Make sure it says DMS unless you want reloadable motor system, which is RMS. DMS is disposable motor system. So you're going to click it. I'm going to show details. This is the thrust curve. Launch mass, this is how much the motor weighs, and this is after it's empty. If you want to know what your propellant mass is, subtract the difference, and you'll be able to find find the propellant mass, which is important because it's about 100 grams, which means with this rocket, with the motors in there, it's below the 1500 grams. It's below the 1500 grams of weight. So federal regulations state that a Class 1 rocket, without needing an FAA waiver to launch, has to be 1500 grams or below, and the propellant weight must be 125 grams or below. So technically you could launch this one without an FAA waiver. So now that we've added the motor, all of a sudden we get numbers. Let's go to flight simulations. Everything seems to be okay right here, but we need to double check something. It says the optimum delay is 8.57 seconds. Velocity at deployment is 35 miles per hour. That's pretty high in my opinion. I want it to be like 10, 15, because this feels like it's going to shred my rocket. So you go to motors and configurations, double click it. Notice it says 7. And if we bring this down, notice the -7. That means 7 seconds into the flight, it's going to eject that. So it's not even going to hit. Let's close that. Flight simulations, time to apogee is 8.5 seconds. So it's going to be before it even hits its peak. So yeah, I could shred it. So we're going to double click it again. Click in here, hit backspace. I'm going to hit 9 and then enter. Then I'm going to hit OK. Notice it changed it to 9. Go back to flight simulations, hit run simulations just to make sure it goes through. And look at that, a nice soft 9 miles per hour when that parachute deploys. Apogee is about 1,700 feet, not bad. Ground hit 16 miles per hour, not bad. Okay, awesome stuff. So that is the basics of using OpenROCKET. Couple of last things. I've shown you this, but let's go to Photo. Nope, let's not do Photo Studio yet. Let's go to Rocket. Double click a component such as the nose cone. Go to Appearance. Change the color. We're going to do black. We're going to hit OK. We're going to click Close. Go to Tools, Photo Studio. And now we have this 3D render of our rocket. Go to Effects. You can put on some smoke. It's hard to see, but you can put on some flame. Put on some sparks. And now we kind of have an idea of, when we paint it, what it's going to look like. I mean, it's kind of cool. What does speed do? Oh, it kind of does a little bit of a motion blur on the fins. Look at that. That's cool. Then there's some other options I imagine under here, but I don't usually use this, but it's kind of cool. Okay, so as I said last time with general, the component finish, aircraft sheet metal, that means it's smooth, it's 2 micrometers. That value is used for skin friction, which calculates, remember I said at low Mach numbers, skin friction is the dominant factor for your drag, and that's why that number is important. So I'm going to go ahead and hit OK anyway. And then we're going to go to File. We're going to print Design Info. And I have all of them selected, but you don't have to. Just preview and print. This is what it's going to show. It's going to show the blueprint, so to speak, of your rocket. It's going to show all this other interesting stuff, bill of materials, template. If you wanted to cut this out on paper and then cut the fins out in wood, you could, or the centering rings if you wanted to. It's always nice to turn into a design report and add it into another technical report if you're writing a technical report for something. But let's see. Okay, so that's that. Is there anything else? Preferences. I showed you how to change the Mach number. Oh, units. Go through preferences. You can set your units to whatever you need. Your simulation, design. That's what I was going to show you. Let's go to flight simulations. Hit run. So that's a green dot. And then go to plot and export. Leave it as default values for just right now and hit plot. This shows you this kind of data: altitude, vertical acceleration, velocity, the apogee, when things are going to happen, each event. You can export the image. You can use this little square thing right here to kind of zoom in to an area, hit it again to back out. Then you can export the data as a CSV, tell it what you want to do. You can change all of these to different types of axis labels, or you can get rid of them completely. Then you can check each one here to what you want shown for the events. You can do stability versus time. Let's do drag coefficients versus Mach number. Why not? Hit plot. So Mach number, we're at what? Right about here. Your drag coefficients, so you can kind of see what happens. Base drag coefficient looks like it's increasing, so higher Mach numbers. Where is there a pressure drag? Yeah, it eventually will. Higher Mach number, it's increasing as well. Anyway, kind of cool. You can name your simulations and then export all the data, and when you plot it, notice it says simulation 1. It'll be named to what you want up there, and then you can use it for a technical report. So, but this program has been used thousands and thousands and thousands of times for high-powered rockets. even ones that go to 300,000 feet, the edge of space. So it's if it's good enough for the edge of space, it's good enough for us. Okay, now I am thinking for right now that's enough for you guys to digest and to mess around with. Next, we'll talk about using mass overrides to control the stability, so we can add a larger motor into this so we can use the same rocket hopefully as a level 2. It does say on Apogee's website that the recommended motor for this is HI and some of the J's, so it should work for a level 2. Anyways, thank you for watching and enjoy.